area vibration in the aerospace lecture series. Today we are going to see the differential equation for dampers free vibration. So here we are using the dampers for the free vibration. Let us take the spring mass damping system. This is a damper and the mass is M and this is stiffness A and this is the damper. So there is an equilibrium. So for this, so we have three an inertia force, damping force and stiffness force. So let us write the equation of motion. It is mx double dot plus cx dot plus kx equal to 0. So let us assume x equal to e power of ut. So let us say this exponential motion of the system is this one is x equal to e power ut and x naught will be u t and x double dot will be u square ut. So now we can replace this x dot and x double dot in this equation of motion. We will get m u square ut plus c u e power of t plus k t. This is t over here, right? So e power of ut equal to 0. So from this we can take e power of ut as common, and then we have m u square cu plus k is equal to 0. So from this equation we have two options. One is either e power of ut 0 or this term will be 0. Anyhow we have taken x is equal to e power ut, then x power u power ut is may not be definitely 0, but whereas this x m u square plus cu plus kx must be a 0. This is a quadratic equation. For this we will get minus b plus or minus root of b square minus 4ac by 2a as the two different solutions for u. We will get u1 and u2. So from this we will get the u1 and u2. Then we substitute in this equation, right? So u will be, this is minus b is minus c plus or minus root of b square minus 4 m into c is k by root of 2m. So this is the solution we are getting. So if we apply this u1 is equal to minus c plus or minus, that is the first term is plus, so root of c square minus 4mk divided by 2m. And solution for u2 will be minus c minus root of c square minus 4mk by 2m. So these two solutions we can use here. Rewrite this equation so u1 will be minus 2 by 2m plus root of c by 2m the whole square minus 4m by 4m square. So we will get 4 cancel and we will get k by m. So this u1 of root will be plus or minus root of c by 2m the whole square minus k by m. So this is solution we are getting. So we can write the x equal to a1 e power of u1t plus a2 e power of u2. If you substitute this, and the displacement will become the large e power of minus plus root of c by 2m the whole square minus k by m plus an2 e power minus c by 2m minus root of c by 2m the whole square minus K by L. So this is how the differential equation we are getting for the damped vibration, and from this we can say whether it is a critical damping or under damping or over damping. When it is a critical and the damping coefficient becomes very critical and this term becomes 0, so we'll get C by Cc as equal to 1 is a critical damping, C by Cc is equal to greater than 1 is a over damping, less than 1 is will be a under damping. This we will see in the next class.